So the last talk before lunch by Vincent Liew towards verifying nonlinear integer arithmetic.
Okay, hello. I'm Vincent, and I'll be presenting joint work with Paul Beam. So let me set the stage real quick. So as we all know, formal methods have been quite successful in verifying many different artifacts of hardware and software. And in many of these problems that we're interested in, they've involved bit-level arithmetic operations very fundamentally. So for example, if we want to verify properties of a cryptographic hash function or ALU designs, these arithmetic operations are fundamentally involved. So we're going to be considering two problems of interest. The first one is equivalence checking. So given two different arithmetic circuits, are they equivalent in terms of input and output? Okay. And the second related problem is specification checking. Given, say, a multiplier circuit or something larger, does that circuit meet its specification? So for example, for this multiplier, if it is implemented correctly, then it should satisfy the distributivity property as well as 1 being the multiplicative identity. Okay. So these specification checking is naturally expressed as a bit vector formula that says that this property is false. If the multiplier is implemented correctly, then this formula will be unsatisfiable. So if we can decide bit vector formulas, then we will be able to solve many different specification verifying problems. Okay, so before I go into the meat of the talk, I wanted to talk about a few related approaches to multiplier verification in particular. So the problem of verifying that a multiplier is correct has a long history that dates back to the 1980s. And even today, it's still considered quite a difficult problem. So one of the approaches that I wanted to highlight is the bottom one here, Grobner basis algorithms. So these are a fairly recent development, and they have been quite successfully used to verify fairly large multipliers. But on the other hand, when we wanted to verify larger systems that only contain a multiplier as a small component, these algorithms don't do quite so well with the non-algebraic components of the verification. This work is going to be talking about a SAT solver only approach. So this is in contrast with the Grobner basis algorithms in that these SAT solvers tend to be highly effective at verifying the non-algebraic components of these problems. And as for the algebraic components of the problem, that's what this talk is going to be about. Okay, so let's go back to our problem of how do we decide a bit vector formula. So the typical way that we do this in practice is to do what's known as flattening or bit blasting to an equisatisfiable SAT formula, and then run a SAT solver to figure it out. How is this done? It's done in two main steps. The first step is to add Boolean variables that capture each bit of each bit vector that appears in the formula. And after you've done that, you add constraints that capture the semantics of the different operations that you're doing on these bit vectors. So for example, if we wanted to flatten the bitwise AND between x and y, all we need to do is add some constraints that say that the ith bit of this bitwise AND is equal to the AND of the ith bit of x and the ith bit of y. So bitwise operations are pretty simple. To flatten arithmetic operations like plus and times, we get our constraints from a circuit implementation of the operation. So for example, in order to flatten addition, x plus y, for bit widths of 1, we can just simply use this full adder circuit. And for greater bit widths, we can chain these full adders together to form what's known as a ripple carry adder circuit that adds together two length n bit vectors x and y. To flatten multiplication, we stack these ripple carry adders on top of each other in order to make what's known as an array multiplier. So this multiplier has two parts. There's the main portion is this tableau, which holds the partial products between x and y. And then these ripple carry adders will take the sum of these partial products, similarly to the grade school algorithm, until it has computed the output bits. Okay, so at this point, it seems like we should be done. Once we flatten to the once we flatten our bit vector formulas, we'll tend to obtain a SAT instance with about a few hundred variables and maybe a few thousand constraints. And our modern SAT solvers are very powerful. They can handle industrial instances with millions of variables and millions of constraints. So aren't we done? Well, it turns out that multiplication as an operation is a major bottleneck to deciding these formulas. So take a simple property that we might want to verify that a multiplier circuit has, such as commutativity. So let's follow our strategy. Let's make a bit vector formula that says that some counterexample to commutativity exists. This formula has the property that if and only if our multiplier is commutative, then it'll be unsat. Okay, so what happens in practice when we try to run SAT solver on the resulting formula? Well, it turns out that our current solvers get stuck at around, they hit a roadblock for this problem at 16 bits. No matter what solver you try to use, no matter what multiplier implementation even you try to use, they all get stuck at this, they all hit a wall at around 16 here. And in practice, in order to get around this, we often resort to treating multiplication as just some sort of arbitrary two-argument function that's uninterpreted, just treated as a black box. But that's often too weak for some of the verification problems that we want to solve. So for this problem, if we treated multiplication as a black box, then our formula would become satisfiable, not what we want. And this phenomenon is not only, commutativity is not some special case. Turns out that no matter what solver you take, whenever you give them a linear arithmetic problem, such as commutativity, associativity of addition, those tend to be quite easy for us to check. Even multiplication by a constant doesn't really pose much of a problem. On the other hand, whenever you throw nonlinearity into the mix, you end up with formulas that hit a similar wall. These are all hard to check for SAT solvers. So this suggests a question: why is this? Are these problems perhaps feasible with better SAT solving technology? Or is there some sort of fundamental barrier that's stopping us from solving any of these? And what would that fundamental barrier even look like? To explain what a fundamental barrier might be, we need to turn to resolution proof complexity. So our modern SAT solvers are based on this resolution rule, which takes two clauses, one with a variable and the other with its negation, and produces a new clause as accordingly. And using this rule, we can prove that a given Boolean formula is unsatisfiable if we can apply this rule over and over and derive the empty clause. So for example, with this formula, we can apply the resolution rule, choose two clauses, resolve, repeat, until we have derived the empty clause. And once we've gotten there, we know that we've proven that our formula is unsatisfiable. Okay, so what does this have to do with SAT solvers? Well, the CDCL algorithm is implicitly actually traversing a resolution refutation. That is, each of the steps of CDCL can be rewritten in terms of applications of this resolution rule. So in particular, if it takes time s for a CDCL solver to prove that a formula is unsat, that means that it has implicitly generated a size s resolution refutation of the formula. Okay, so this fact leads us to this conjecture. Maybe these SAT solvers are taking so long to solve these problems because the resolution proofs need to be exponentially large. Okay, so why else might we believe this? There are other similar problems that have been proven to have large resolution complexity. So take this mutilated chessboard problem on an n by n grid. This board can't be covered in dominoes because each domino covers one white and one black square. So if you encoded a SAT formula that says there exists a covering, that formula would be unsatisfiable. However, to prove that fact in terms of resolution, these proofs require exponential size. And these multipliers seem to have similarly grid-like features to the mutilated chessboard problem. So most multiplier implementations are going to involve a tableau of partial products, as well as adders that enforce, again, local parity constraints, similarly to the mutilated chessboard problem. Okay, so our result is actually that the conjecture is false. Great news. Proof size is not a roadblock for us. So we found that actually for any degree 2 bit vector identity, for example, commutativity, distributivity, and so on, we found polynomial size regular resolution proofs when we use array, diagonal, and Booth multipliers, as well as quasi-polynomial size proofs when we use Wallace tree multipliers. In terms of equivalence checking, we also obtain results that give polynomial size proofs for the equivalence between array and diagonal and Booth multipliers. And if we are trying to figure out equivalence with a Wallace tree multiplier, the proofs are quasi-polynomially large. Okay, so those are our results. What do our proofs look like? So our proofs actually fall into a special class of resolution called regular resolution. And to sum it up, basically these regular resolution proofs are read-once branching programs. So to see this, take each clause that appears in your regular resolution proof, map it to the forbidden assignment, so as shown, and then the operation of resolving on X turns into the operation of branching on X. What is this branching program doing? It's solving the conflict clause search problem for phi. This problem is, given an assignment, find a falsified clause in the formula. So this branching program, you can imagine as you start at the root, you follow the arrows according to whatever assignment you're given, and once you reach a leaf, that tells you which clause in your formula has been falsified by your assignment. Okay, this conversion actually goes both ways. So if we're given a size S FBDD that solves the conflict clause search problem for our formula, that's isomorphic to a size S regular resolution reputation for the same formula. And so the proofs that we present are going to be in the format of a polynomial size FBDD that solves this conflict clause search problem for our formula. Okay, so let's see an example of what our proofs look like for the case of multiplier commutativity. So let's make our instance. We fix some input bit width, and we construct the bit blasted formula, which has 2 copies of the multiplier. One copy computes x times y, the other computes y times x. And then those go into another circuit that just says that there's some output bit that differs between the two. Okay, so the first step of our branching program is going to be to branch on the output bits to find the first one that disagrees. So we start from the lowest order bit, go forwards, as long as we find it, until we find an unequal bit right there. This gives us this basically case splits our verification problem into 2n different sub-problems. Okay. But it seems like we encounter this problem if we try to write our branching program here. The problem is that this high order output bit is sensitive to all the previous entries in our tableau. So if we flipped, say, the second bit from the second column, it could cascade and propagate to cause this disagreement in our final output. Okay, and if we tried to store all the entries in our tableau, this would require an exponentially large FBDD, too big. So how do we get around this? The first key idea is that all we need for our formula to be unsatisfiable is what we call a critical strip of the prior log n columns in our multiplier. So what we can do is just focus our attention on that narrow strip, just throw away all the other constraints. throw away almost all of the constraints, this instance will still be unsatisfiable. So this is clearly like a major simplification of our problem. We've eliminated almost all of our multiplier, and we've reduced our problem to proving that this smaller instance is unsatisfiable. Okay. The second key idea is that each of these critical strip instances actually has a polynomial-sized regular resolution refutation. So why is that? You can see it if you know of this path width argument. If you look at these graphs, the constraint graphs, they have order log n path width. And it turns out that we can find resolution proofs that are exponential in the path width and hence polynomial in size. In our paper, we actually will give explicit polynomial size FBDDs, and we do that in order to give actual explicit size bounds for these different problems. Okay, so combining these key ideas, 1 and 2, we obtain a proof that looks like this, sort of a right linear tree, where on the spine we just query these output bits until we find a bit that disagrees. And once we find that disagreeing bit, we go into this poly-size critical strip refutation. And of course, combining all those polynomial size proofs, there are 2n of them, our overall proof is also polynomial in size. Okay, so these two key ideas get these are some of our explicit bounds for these proofs. Our key ideas actually apply to any degree 2 identity. All of these can be broken up into critical strips, and they yield refutation sizes as shown in this table. All right. And we think that this is a very promising direction for us. So we think that this brings maybe some hope to verifying nonlinear arithmetic problems. The path forwards, we think, is to first improve our solvers to find these small proofs. So we've done some preliminary work. It's very early, but so far we found that just taking the critical strip instances and feeding those into the solvers is not quite enough. They still don't perform too well in those critical strips. But once we've done this, improving the solvers, then we would move on to verifying larger scale problems, which maybe include a multiplier as just a small component of a circuit or program. And then there's also this open problem of finding the small proofs of for associativity. This is a degree 3 identity. And so far, we're not sure whether this has small proofs, or maybe there's some sort of, maybe they require exponentially large resolution proofs. Okay, so this is the last ring property of multiplication. We've proven all the other ones like commutativity and distributivity. This is the only one left. So we think that maybe if we can get a proof for this, we may be able to get small proofs for any polynomial bit vector identity. Okay. Or maybe degree 3 is a barrier for resolution. This is open. Yep. Thank you. So that's all. Yep.
Okay, questions?
Hi, thanks for the really good talk. Don't you run the risk of proving that factoring is polynomial? Because you've got a polynomially sized proof, and I can ask the question, is P times Q equal to my RSA key? And unit propagates polynomial, so...
That's a good question. So just because there's a proof, there's an element of non-determinism here. So given our problem, the proof is sort of like you can think of it as a certificate for our formula being unsatisfiable. So it seems like it might fall in a similar complexity class as factoring in maybe NP, so to speak. Yeah, I'm not quite sure how you would express factoring as a specific problem in here, but that's actually quite interesting, so maybe we could talk more about that.
Yeah, that was the problem we were running into on designing better multiplier bit blasting encodings, is that, yeah, we have some concerns around that, so it'd be really good to talk. Cheers.
Cool, yeah, that's really interesting. I'll be happy to talk.
Any more questions? If not, thanks to Vincent and lunch.
Okay, thank you.